So this is problem 8.40 from the text in the homework, and in the book we have a radius. So we got a car taking a highway curve that's banked at 15 degrees and with a radius of 70 meters. That's pretty sharp, but let's stick with it. So free body diagram, we have the r-axis and the z-axis, not x and y, r and z, and we're the net force points in the r direction. What's free body diagram look like? Oh, by the way, the mass of the car, it's going to be irrelevant in this model, but the mass of the car is 1,500 kilograms. And so what's the FBD look like? We got mg down. Mg down, we have normal force up, and it makes a 15-degree angle with the z-axis. And here's what's tricky is that, right, I mean, there's a friction force down, and it makes a 15-degree angle with the r-axis. So that's 15. And this friction force is F sub S max, because it's the maximum speed with which we can take this curve any faster, and the road cannot provide sufficient static friction to keep the thing from sliding upwards. So that's free body diagram. So summing the forces in each of the directions, we got the r-axis and the z-axis. Got to be careful with the cosines here. We got a cosine, we got a 15-degree angle. I'll just do regular theta. So in the r-axis, we've got plus n sine of 15 degrees plus static friction max times cosine of 15 degrees. And that equals, I don't have enough room, it equals mv squared of r. I'll just squeeze these last few parts. Oops. As plus, so this is f sub s max times cosine of 15. That equals, I got enough room here now, mv max squared over r. I guess I wrote little one. And then that's the sum of the forces in the r direction. What about in the z direction? You have n cosine of 15 minus static friction max sine of 15. That equals mg. Technically, it'd be minus mg equals 0, but I mean, that's how you set it up. Okay. So the trick in this example is to take f sub s max, because f sub s max, as you may recall from chapter 6, is equal to the coefficient of static friction times the normal force. Coefficient of static friction for rubber and concrete is 1. So that's easy enough. So replace the static friction with mu times n. Oops. Get the eraser. Let's see where we're at right here. Right. So this thing is replaced, and this thing is replaced. So we replace that with mu times n. And so you see both of these equations will now have a normal force in them that you can factor out. So this would be mu, both of these are mu sub s times n. And now what I recommend is that you factor out the normal force in each of these equations and then divide. And that's nearly all you need to do. So if you factor out the normal force and then divide, what you'll get is cosine 15 plus mu sine of 15 divided by, yeah, I had that wrong, sorry. Sorry, sine of 15 plus mu cosine of 15 divided by cosine of 15 minus mu sine of 15. And when you divide the right-hand side, the mass is canceled as I said, so you get v squared over rg. And so you can solve for v, multiply by rg, and take the square root, so you get v max equals that thing, right? That's sine of 15, sine of 15 plus mu cosine of 15 divided by cosine of 15 minus mu sine of 15 all times rg, and then all of that is square root. That ends up being your expression for the maximum speed of a car taking that specific bank curve with that specific radius.